Okay, I think we're ready to start. So before we'll continue with the panel discussion later, we'll have two more exciting keynote talks coming up. And the first one is by Marilena Loverde from the State University of New York at Stony Brook. And so Marilena has a wide range of interests between early and late time cosmology, studying physics from the CMB over neutrinos, halo biasing, and so on. But I'm particularly interested in her talk today about new techniques and for new physics in large-scale structure. So please, Marilena, go ahead.
Thanks. Thanks to the organizers for having me at this conference. It's been really interesting so far, and I'm looking forward to catching up on talks via YouTube that were at inconvenient times in my time zone. So I just wanted to mention, I'm actually moving from Stony Brook University to the University of Washington, which will be, I'll live in a city with water and mountains, and we have a new cosmology and particle astrophysics group that we're building up there. So I encourage you to consider us for sending PhD students and postdocs and so on. Today, there we go. I'm going to talk about new physics in large-scale structure, new computational tools to study this physics, and I'll wrap up with discussing some new observables. So let me step back and give an overview that was somewhat covered by a number of talks already, this morning's nice talks, but from a slightly different perspective on looking for new physics in large-scale structure. So very generally, our goal is to find new physics in galaxy surveys or intensity mapping surveys or lensing surveys. And our observables are things like the number of objects at different spatial positions and at different epochs in cosmological history. And examples of the new physics that we hope to detect is evidence for primordial non-Gaussianity, which could tell us, for instance, that the structure in our universe was generated by some other light field that's not the inflaton. We hope to measure at good significance the absolute mass of the neutrinos, or detect ultralight axions, or some other novel physics that's present as warm dark matter, or some conflict between cosmological data sets and laboratory experiments that would tell us there's a non-standard neutrinos and so on. Or we hope to detect some deviation from general relativity and a cosmological constant. In order to do this, we need really, really good control over the predictions for our observables, because the types of signatures that we're looking for produce very small changes to the things that we actually measure. For instance, detecting primordial non-Gaussianity at the order of FNL of 1 requires something like nothing other than this primordial non-Gaussian signal modulates the galaxy distribution at the level of like 1 part in 10 to the 4. Measuring the sum of the neutrino masses at the minimal mass normal hierarchy would require that we can predict the fluctuations in the baryon and cold dark matter density to something like 0.4%. Deviations from general relativity and a cosmological constant are even harder because there's no firm threshold that we're looking for. And we may even have a strong prior that they don't exist. So we need really good control over predictions for these observables, or predictions for particular statistics that are robust, predictions for changes to particular statistics in the presence of these sources of new physics that are very robust at this level. So how is this physics imprinted in large scale structure? Well, information about inflation is encoded in primordial fluctuations, for instance, the primordial curvature field, or maybe if there's different types of matter density are allowed to fluctuate independently, we could have isocurvature fluctuations. And the quantities that we can measure to learn about this era are correlation functions. So 2-point functions, 3-point functions, and so on, or cross power spectra if there's independent fluctuating quantities. The things like matter densities are all proportional to these primordial fluctuations. And the thing that determines the proportionality at the linear level is just these transfer functions. So the transfer function for some type of stuff, some matter stuff X, the transfer function is just the linear theory solution to the Einstein and Boltzmann equations. So the information about the types of energy that are around, for instance, the sum of the neutrino masses or the expansion history of the universe is encoded in these transfer functions. The things that we actually measure are more complicated than this. They're always nonlinear functions of the matter densities, and therefore these primordial fluctuations and the transfer functions and the things that we can understand better. Yet these observables that are complicated nonlinear things, their spatial variation is still predicted by the spatial variation in the different matter fields. So for instance, fluctuations in the abundance of galaxies at position and at different epochs in time are set by fluctuations in the cold dark matter distribution and the baryon distribution and so on. Whereas Fabian mentioned, this would be sort of the coarse-grained fluctuations in the matter distribution, coarse-grained on some scale, which describes the characteristic scale of the observables that you're looking at. So then fluctuations in our observables will follow fluctuations in matter. So the correlation functions and the things that can be measured are still proportional to correlation functions in matter that we understand better. And this proportionality coefficient that will appear here is referred to as the bias of the observable. And that bias is some property of the observable. So galaxies of different mass or luminosity or color will have different bias factors. Different objects like voids will have different bias factors and so on. So now I'll talk about computational tools that we've been using to study these quantities. And this is the so-called separate universe or response approach. So the idea here is that a subset of nonlinear quantities that we care about involve responses of these observables to long wavelength fluctuations. So here I have some observable O that varies from at different points in space and time. And the spatial fluctuations in that observable can be set by spatial fluctuations in the matter field. So in some overdense region, the observable has its global mean value plus some term which depends on how this observable O responds to the matter density. And in the underdense region, I have the opposite. Now, an observer looking out at the universe measures correlation functions of this observable, for instance, and the correlation functions of this observable are then set by correlation functions in the matter field with some coefficient that depends on how the observable responds to the matter. So this is useful because sometimes observables themselves are hard to predict and infer cosmology from on their own. For instance, the number of galaxies on average in the universe is not something that we usually extract cosmological information from, yet the spatial variations in that seem to be a more robust tracer of physics through the large scale spatial variations in that linearly trace fluctuations in the matter, and so we can extract information from that. So the trick here is that if the characteristic size of this observable is small compared to the spatial variations in the matter field that we're looking at, then one can absorb the fluctuations in the matter into a change in the local background for the observable. So let me rephrase that. So here is my fluctuation in the mass field, which contains the information about the physics that I care about. And here's some observable, which could be numbers of galaxies, halos, voids, or other more general things I'll talk about later. And if the size of that nonlinear observable, if the particles that make up this nonlinear observable all come from some small region that's small in physical extent in comparison to these large scale matter fluctuations, then the dynamical effects of these the matter fluctuation can just be absorbed into a change of coordinates. So what I mean by that is if I'm a little observer sitting here, then I can redefine my local coordinates so that my local co-moving coordinate includes both the global expansion history of the universe plus some change in the expansion rate and due to the dynamical effects of this matter density. So in a universe with just cold dark matter, things expand a little bit more slowly in an overdense region than they do in an underdense region, for instance. And this works for, I'll repeat this again, observables of characteristic size small compared to the fluctuations that we're interested in, which is anyway the regime where we think that we have more robust predictions, where we separate scales from nonlinear stuff, small scales, to linear large scale physics, and cases where I'm only interested in the isotropic response of this observable. So this would be the linear bias factors that Elizabeth mentioned. And so I can do this, and then if I study, for instance, the particle equations of motion in some little region, they look like the normal equations of motion for particles in an expanding universe, but the local Hubble rate and the local scale factor are modified by the presence of this background mode. Okay, so this is a trick called the separate universe approach. And this is useful because then I can predict these responses or the bias factors of these observables by comparing how the observable, what the observable looks like in the cosmology in the over or underdense region with the modified scale factor and Hubble rate compared to the observable in the global universe. So if I have a way to compute this observable for different cosmologies, then I can compute the response straightforwardly. And this is in comparison to measuring these quantities via clustering. So for instance, I can compare how the observable would evolve and in the presence of a long wavelength mode, or I can measure spatial correlations between my observable and matter density fluctuations in different places. So comparing these two should agree and verify that this approach is doing the right thing. These types of relationships look similar to this large-scale structure consistency relations, which are derived from residual symmetries of the equation of motion. And this separate universe approach is sort of similar to that. I think it's a little bit of a generalization in the sense that these consistency relations are finding residual symmetries, the equation of motion, where the physics is not changed at all. And in this case, the equation of motion is changed. There is a dynamical effect of these large scale modes, but the new equation takes the same form as the old equation, just in a different cosmology. So these modes have physical curvature as opposed to being some kind of residual gauge modes. Okay, so then if one has methods to compute these observables, you can just do that. And so you can do that via analytic methods. If you have an analytic prediction for the observable, for instance, studying how the linear growth of fluctuations in different regions, you can just change the linear growth equations to linear growth equations in a new cosmology to compute how the power spectrum would respond to different, to the long wavelength mode, which would give you some part of the squeeze limit bispectrum. Or you could use a spherical collapse, for instance, to predict the number of objects in different regions. Or you can just use n-body simulations, and then you can compute anything you want. So for instance, this cartoon illustrates running n-body simulations with modified expansion histories that account for the dynamical effects of being in regions with some background density. And it's important to note that this modified cosmology that you input in general depends on the full evolutionary history of these background matter fluctuations. Not just generically, they don't just depend on the background matter fluctuation at a fixed time, but actually you care about the full evolutionary history, which I'll mention more about in a second. So why do this? Well, you can do this. There's some specific advantages are that you get some cleaner measurements of these responses or these bias functions. And that's specifically because I can run these simulations with the same realization of the small scale power spectra, the same realization of the small scale fluctuation. So I take the same initial conditions here, the same initial conditions here, but just change the background expansion history. And then the cosmic variance due to different realizations of small scale modes cancels. So that tends to give a cleaner measurement. I also get an easy method to compute responses in the presence of different types of matter or for different realizations of the large scale matter fluctuations. So what I mean by that is I can run simulations where I mock up the expansion history to account for being in a background with cold dark matter, with some new stuff like weird dark energy in the background of neutrinos, or even radiation. And I can compute all of these effects without writing a new code that simulates both dark matter and this stuff. I just need to account for all of this stuff in the local linear theory evolution of the background modes, which changes the local cosmology. I can also compute it for these quantities separately, or for any particular, I don't care about the large scale realization of these fields. I can do it mode by mode. So I can compute the response for an individual Fourier mode, and then I can sum all of those responses to get the net effect in our universe, for instance. So I don't need to know the large scale. Let me repeat. So if I was measuring quantities via correlation functions, I need to know the large scale correlations in the matter field, for instance, or the large scale cross correlations between matter and other stuff. But if I'm doing this response approach, I just need an individual mode in the matter density field. I don't need to know how the matter density field is correlated on large scales. So that simplifies things most explicitly if you were caring about some new physics like isocurvature. This approach also gives some insight into how observables care about the background matter density, which can help you identify signatures of new physics. So this has been done in a number of scenarios. This has been done in Einstein de Sitter and lambda CDM cosmology. I realize I left off that part with lots of important references, including by people in this audience, but I cite them again later. But it's been generalized to cosmologies with neutrinos and cold dark matter. Photons are other sources of radiation in cold dark matter. Scenarios with clustered dark energy, isocurvature and cold dark matter, or even compensated isocurvature modes, which is somewhat of a distinct case because it's not quite changing the expansion history in the same way, just changing the local parameters. I think this is interesting, and I want to spend 1 second just emphasizing why this is useful for these approaches. So these non-standard cases going beyond just cold dark matter or cold dark matter and cosmological constant were first done by my group and by collaborators. And this is not just weird cases. This is really our universe. So including cluster dark energy is not our universe, but neutrinos definitely are our universe. So so I think that's important. And it also highlights, this technique highlights the importance of the history dependence of structure formation in the following sense. I'll just mention this briefly. So if I have different types of matter around, or variations in the initial conditions by, for instance, having both adiabatic modes plus isocurvature modes, then I can have matter fluctuations with different evolutionary histories. So what I mean by that, this is distinct from Einstein de Sitter or lambda CDM cosmology with just adiabatic initial conditions, where in the linear regime, every mode evolves in the same way. If I see some density fluctuation at a fixed time, I can tell you, all I need to know is the amplitude, and I can tell you how that mode will evolve in the future or how it was in the past. If I have different types of matter around, then I need to know both the amplitude of the fluctuation, but also the density profile and what other types of matter are present, even if they're fluctuating coherently. If I have isocurvature around, I need to know not just the amplitude at a fixed time, but I need to know the initial conditions, how much of that mode is comprised of adiabatic versus isocurvature initial conditions. So I can have linear theory density fluctuations that go through different evolutionary histories, and that will therefore lead to different local expansion histories. An observer in the presence of these different modes will see different histories of A and H, for instance, which will therefore impact these observables differently. So this leads to the existence of new observables that now depend on, it makes these observables now depend on both the relative composition for isocurvature initial conditions, for instance, or wavelength for scenarios where I have adiabatic initial conditions, but scale-dependent growth due to the different types of matter. Okay, so this approach has been used for a number of different cosmological scenarios and also for a variety of different observables. So the first works on this were done to compute response factors and therefore halo and bias for halos and the small scale matter power spectrum. So giving again the halo bias and part of the squeeze limit matter bispectrum in these works. It has been extended to study voids by both my group and Nico's group, and more recently to study the probability distribution function of matter and halos. So I'm going to spend the next few minutes, the rest of my time talking about this new work. I can't see if there are any questions. I'm happy to be interrupted for questions.
Yeah, please raise your hand whenever you have a question.
Okay. Okay, so now I'll talk just about this one example of a new observable. It's actually two new observables in different scenarios. And this is work led by my really excellent graduate student, Drew Jameson, who's pictured here, in two kind of companion papers that just came out in the last few months. So in this case, what we study is how the probability distribution function for matter and halos varies spatially, and how the spatial variations in the probability distribution function are sourced by spatial variations in the mass distribution, which is perhaps not surprising. So in this first paper, we study the probability distribution function of the matter field and what's referred to as the Eulerian PDF. So let's just look at the top panel of this plot for now. And this plot shows the probability distribution function. Let's look at the black dot dashed curve here for mass fluctuations. And this is mass fluctuations smoothed in spheres of radius 10 megaparsecs. So I take my matter field and I smooth it on this scale. And then I measure the value of the density fluctuation in spheres with this radius. And that's the variable on the x-axis. So this is fluctuations in the mass density, smoothed or windowed on some scale. So the black dot dashed curve is the probability distribution function for all the matter in the whole simulation. These different curves illustrate what the probability distribution function looks like in regions that are overdense in red and underdense in blue. And the value of the background density is shown here. So I take a big simulation or a big chunk of the universe and I divide it into little regions and I measure the probability distribution function for mass fluctuations in a little region. And that little region will have a different background density than the global universe. So in this case, this density fluctuation is measured with respect to the global universe background density. So the mean shifts, the mean density shifts, and that's visible on the peak. But also the overall shape of the PDF is changed. So I have in overdense regions, I have fewer underdense, small scale underdensities, but many more large scale underdensities. So this illustrates the spatial variation in the PDF as a function of the local density. One thing that we found here is that this response quantity, so the spatial variation in the PDF, is much more accurately predicted than the PDF itself. So on the top set of plots are plots of the PDF overall in simulations versus a model. And you can see this is a simple model, and you can see that they agree relatively well, but mostly near the peak. But once you get towards the tails, this is a log scale. There's a big difference between the PDF and simulations and a simple model. On the other hand, this quantity, the response, the logarithmic derivative of the PDF varied from place to place, is much, much more accurately predicted. So that's kind of nice. And this is interesting because another way to think of this position-dependent PDF and this response quantity is it's like you're measuring the bias of regions in the density field selected based on density. So again, this quantity is the low density flux field smoothed on scales of about 10 megaparsecs. So the mean value is here at 1, and these underdense regions are things that would end up in voids, and the overdense regions over here are parts of the density field that are in halos, for instance, as you get to much higher values of the density. So this is like, rather than measuring the bias of halos or the bias of voids, this is like measuring the bias in all stuff based on fixed density and getting all of that information. And it's interesting then that the bias of this PDF is, you can actually predict it quite accurately from this model. So it's more accurately predicted, for instance, than the bias of galaxies. Though this is all matter, there's no, this particular plot doesn't include halos or galaxies or anything yet. But the fact that this is predicted pretty well means that you can do things like see how the response depends on different cosmological parameters, for instance, neutrino mass. So this is a plot showing how this response contribution to the bias is sensitive to different values of the neutrino mass. And you can see the most underdense regions or the most overdense regions are most sensitive to changes in cosmological parameters, which is perhaps not surprising. So that is one probability distribution function that you can study. Another thing that we studied is the probability distribution function measured in a different way. So if the previous sets of plots showed the probability distribution of matter fluctuations measured in equal volumes, and the different volumes, they're all the same volume size, but they have different amounts of mass in them. And so we measure different densities. You could do something complementary to that, which is instead measure the density field in regions of unequal volume, but fixed amount of mass or fixed amount of halos. And this is done using what's called a Voronoi tessellation. So this is a plot from our paper and just illustrating what this is. So on the left side, this plot, all these blue dots show the positions of halos. And these cells here show a Voronoi tessellation of this volume. So the Voronoi tessellation is a partition of the volume or the area here into regions with fixed number of objects. So each cell here has one halo in it. And so the volumes are different sizes, but they have a common number of objects. This is for halos. These right plots over here with the red show the Voronoi tessellation of the matter field, in this case illustrated within this little tiny volume here. So I look around a halo, that halo is here. This is the Voronoi cell of the halo. And these red objects show the partition of that volume into regions of fixed mass. So this is a different way of measuring the probability distribution function, and it is somewhat more related to measuring the probability distribution functions for regions and selected on Lagrangian volume rather than Eulerian volume because it has regions of fixed mass as opposed to fixed volume. And the Lagrangian density field is the density field measured in regions of fixed mass. Okay, so this shows a different way of measuring densities by selecting them on unequal volumes. And from that, one can also measure the probability distribution function for matter fluctuations, or in this case, halo fluctuations. This is something that's really straightforward to do with halos because given a halo catalog or a galaxy catalog, you can just come up with the partition for the volume and then measure the PDF. The same thing here is done for the matter field in the simulations. These plots are analogous to the plots that I showed a few slides back, where the black dot dashed line shows the probability distribution function for measured using the entire simulation volume or the global value of this quantity. And then the different curves with different colors show what the probability distribution function looks like if you're just in a restricted volume with a fixed background density, which is illustrated up here. So again, overdense regions are red and underdense regions are the PDF and underdense regions are blue. And the fractional difference between these quantities is shown down here. We show the same thing, but for the probability distribution function of halos. In this case, the tessellation that you arrive at will depend on the halo catalog that you start with. So we have halo catalog of a fixed mass. You get a fixed tessellation, and then you can measure the probability distribution function there. And this one is quite a bit noisier than the mass PDF, but you still can isolate how the PDF is changed by being in regions that are overdense or underdense. We can study this spatial variation in the PDF based on density, again, in two ways. We can use the separate universe approach, where we compute that response by computing the PDF in different cosmologies, a cosmology that's mocked up to account for the dynamical effects of being in an overdense region compared to our standard cosmology. Or you can measure this response quantity by comparing the spatial variation in the PDF and how that's correlated with spatial variations in the matter fluctuation, dividing out by the spatial variations in the matter fluctuation itself. So of course, we really do this in Fourier space and isolate the low K limit of the bias. But the point of this plot is to illustrate that these two approaches agree really, really well over an enormous range of densities. So here we have separate universe measurements of this sort of bias factor of the PDF selected based on density, compared to traditional clustering measurements, which are the red curves. And they agree across like 5 or 6 orders of magnitude. So I think that this is the strongest test of the separate universe approach to date, and that work studying just halo, for instance, the separate universe approach with halos would be restricted to looking at really high density tails, versus voids would be this very low density region, or the matter power spectrum response compared to the position dependent power spectrum or the squeeze limit isotropized bispectrum would be looking at regions closer to the mean density. But here you see the whole thing across many orders of magnitude. Okay, so wrapping up, to look at for new physics and large scale structure, as was emphasized by the earlier talks, you need extraordinarily accurate predictions. And you also want observables that are that isolate the new physics that you're looking for, or are robust against nonlinear evolution or baryonic physics and things that we can't control at small scales. Sorry about that. This separate universe response method provides really clean predictions for these bias factors, and can also help identify robust observables in the sense that you can look for observables like scale-dependent biases from primordial non-Gaussianity, or from scale-dependent growth of density perturbations due to massive neutrinos or other things that persist in large-scale correlations of things and can be detected without knowing the actual amplitude of the bias factor. This approach also allows you to simulate a limited set of important observables, meaning bias factors or squeeze limit correlation functions in cosmologies, even in scenarios with multiple fluids and non-gravitational forces. You can also, this PDF work shows that you can, I think you can think about more generalized bias factors rather than just correlation functions of numbers of objects for more general observables. Of course, that work is not yet, that's using simulations in a very idealized sense, and not yet taking into account all kinds of complications, things like Elizabeth mentioned, and this approach survives very strong tests. So thanks.
Thank you very much for the nice talk. Give a round of applause. Are there questions? Okay, Alex, the first one, please.
Hi, thanks. Throughout, I was wondering, but I was trying to guess what the impact of baryonic effects would be on some of the measurements you had. So I have a question on if you thought about that. So for example, maybe this is a naive intuition, but you tell me if I'm thinking it wrong. If I'm inside a long wavelength mode, I would expect AGN feedback to be stronger. This could smooth out some of the enhancements on the high tail of the distribution. So I would think maybe this would imply a weaker response of the PDF at the high density tail. Does this make sense?
Yeah, that's an interesting question. So I think, yeah, that's an interesting question. So I think that, let my first response would be that I think that so it depends on the scale that you're pushing to here. And for instance, in the Eulerian PDF, it's very clear that there's a uniform smoothing scale and you choose it. And when the smoothing scale gets small, then I would worry more about those types of things. So long as the smoothing scale is large compared to the baryonic gene scale, large-ish compared to the baryonic gene scale, I would worry that it's a good point. So I would worry that for instance, the shape of the PDF would be much harder to predict once you get to those places. I'm not so sure. You might, and therefore the response might also not be so well predicted because this is all dark matter only. It's a good question. I don't know. You may benefit from. It's a good question. I don't know. It could be that the response is not so sensitive to that physics, in particular, since you're sort of like taking the logarithmic derivative of this quantity with respect to the background mode, that if there are baryonic effects, for instance, that they, some of the things that go into this model just don't change at all with respect to the background mode. So because
we have this separate universe simulations with TNG. And there we looked at for example, for the case of power spectrum responses, we also find that the response function is not that affected by baryonic effects. But I was not sure if the same thing can happen at the PDF. It's easy for us to check that. I was just checking if it would be.
Yeah, no, it's not something we don't have simulations of baryons. So in fact, it's not something I've checked at all. It would be interesting to look into that.
Okay, thanks.
We have more questions. Alex Gao is the next one, I think, came up with a question.
Hi, my question is actually about the slide that's up at the moment, so that's quite convenient. So this slide shows that the prediction of your response function is tighter than the prediction of the PDF itself. I was wondering if you could just say a little bit more about what the model that's used for.
I'm sorry. I realized I forgot to put the reference on here. So the reference that Drew, my student, used is this paper by Misha Ivanov and Sergei Severikov. And so that paper includes a sort of more sophisticated calculation of the full PDF. To do this response, he just used the saddle point approximation, I believe, for that. So the nice thing is, you could do a simple calculation where you say the initial conditions are Gaussian, and then you map from initial density fluctuations to final time density fluctuations using spherical collapse. And that's very simple and it doesn't work very well. And then they go through a long exercise to improve on that. And a lot of what that does is change quantities that don't change at all, that are very insensitive to cosmology. And so they just don't show up here.
Mm-hmm. Okay, great, thanks.
There's a question by Eva. Is it Eva Silverstein?
Yeah, hi Marilena. Thanks for the great talk. I have a question that may be totally off base, but let me ask it anyway. So some reasonable quantum field theories describing early universe physics would predict rather heavy tails of the primordial distribution. Is that something that's in range of testing using your PDFs, or is that far from reach?
It's interesting. So I think, there are other people on this call who have actually done more work towards using the PDF towards data than I have. This is just theoretical, using comparing models to simulations, so including none of the complications with data. So they might have something else to say. I think so there's a lot of work. So first of all, there's more work that needs to be done to compare theory of PDF to data. It is an interesting question. I mean, clearly the responses to these quantities are much larger in the tails. So if you had something that made a very different tail, and perhaps the actual PDF itself, once you get to the tail, is very hard to predict. So if you saw a big tail in the PDF, you might not be sure whether that was new physics or you just had a bad model on that side, but perhaps the response is more accurately predicted. So it might be interesting to ask whether this would be a more robust observable for that case. But more work would need to be done.
Thanks.
We still have time. So Blake, I think, is next.
I'm not sure this makes sense. So since you talked about sort of the bias of the PDF and the different bins, have you thought about whether this could be used for sort of multi-tracer methods, like the different bins, and how you would do this, or is,
Oh, I see. You
is
mean
there-
like using the different bin, this bin is one tracer and this bin is another tracer kind of thing?
I mean, or would that even be naturally included if you did a full analysis of the PDF with the full covariance?
Yeah, it's a good. I mean, so as you know, the multi-tracer analysis, you don't have to do anything special. Once you divide up your sample into multiple bins, and include all the cross power spectra, you don't need to use any new statistics, right? Just the cross power spectra show up. So, but I guess, okay, so in some sense, what this plot is showing, it's not showing actually the full bias, but it's showing one contribution to the bias. And that's different from the observable that you measure would then be, if you're measuring the cluster PDF clustering, then you would have, I think the question comes down to, if you measure PDF clustering, then you're measuring the correlation between the PDF here and the PDF here. And then as long as you include different density values, if that makes sense, then you would naturally get all of that.
You just have to include all the covariances between all the.
Yeah, exactly. I think so. This is just showing like one bias factor. So you would have to measure the spatial correlation of the PDF for regions of this density cross-correlated with the spatial variations of the PDF for regions of this density plus, let's say, this density. And then I think then you should include up to treating the covariance correctly. That should be equivalent to doing multi-tracer analysis.
Lam, you had a question?
Yeah, I have a question. Thanks, Marilena, for a nice talk. I have a question actually related to Eva's. If I understand correctly, the way you define the response function for the PDF appears both in the numerator and the denominator, right? So
yeah, this is somewhat schematic, but yeah, it's the logarithmic. Here's a logarithmic response.
Exactly. And so in some sense, what it's measuring is, as you nicely explained, as you change the large scale power or the large scale amplitude fluctuation, how does the small scale fluctuation respond to that? To the extent most of the power on small scales really come from basically gravitational instability, it follows from basically transfer of power from large scales. Probably the response itself is not too sensitive to whether the initial probability distribution has long tail or not, because it's really, the response is really, in some sense, characterizing the gravitational response.
So, I'm not sure if that's true in the sense that, I think that's definitely true, but I'm not sure what dominates. So for instance, the simplest example of computing the PDF response that I might do analytically is to ask how the variance, I might take summary statistics of a PDF, like the variance or the skewness or the kurtosis or something. And in this case, it's all Gaussian. And so the variance is the only thing that matters. And I know how to, I know that the variance changes with respect to the long wavelength mode. So some large part of this PDF response is just coming from the change in the variance with respect to the long wavelength mode. Now, I don't know, and that's all that's more or less the only thing that should matter, the thing that should matter most for Gaussian initial conditions. But if I had some really non-Gaussian tail, I could imagine that there's some other statistic that, I could imagine in general that there are other summary statistics for the PDF like that, like the area and the tail or some other cumulants that would change differently.
Yeah, I agree with you. So if you focus on the variance, then in some sense, the response is basically some version of the squeeze by spectrum.
Yeah, that's part, that's right.
Yeah, but probably if it wants to get at some sensitivity to the initial PDF with some long tail, perhaps, probably one wants to look at the same statistics that you're looking at, but as a function of scale, probably.
Yeah, we have, so I didn't include plots here, but there are plots in the paper. So that was the Eulerian plot, but this, sorry, the Lagrangian plot, but this Eulerian one, so this is on smooths on a fixed radius, and these responses for cosmology here are computed for a fixed smoothing scale, but if you vary the smoothing scale, for sure the response changes as a function of density, and the sensitivity to cosmological parameters changes. And there's some, Drew made some nice plots of that are in our paper.
Nice. Thank you.
Thanks.
Okay, thank you. I think we should move on from here. So thanks again for this nice talk.
Okay, thank